uh, let me ask.
Yes, sorry, sir. I have started recording.
Okay. So those are the preamble. Thank you. Huh? Okay. Is it Mitali? Okay. Thank you. Now, what I am trying to say that your NMR, you have the two-dimensional, all the features are there, and by which you can understand the things. But in EPR, you do not have that kind of luxury in the beginning. But there are options to handle it. For example, I have been repeatedly telling you that simulation is one of the options, and if you can do the same, which is a little bit crude in my opinion, because it depends on what kind of inputs you are providing into the system, and inputs require expertise. Sometimes it fits quite well, sometimes for a complex situation it may not be that good, but after a lot of practices one could have a fairly well resolved and good matching simulated spectrum. Now, other option, if you are very serious from the physics point of view, then pulse CPR one can go into, but that's not very much useful for the chemist. So only options we have in hand your this thing. Now you have seen that how the it gets splitted, etc., etc. All sort of things we have already talked about. We should not go into the same repetition. But then we moved into the relatively simpler situation where you are unpaired electron in an organic molecule, and you have the options of hyperfine, super hyperfine, all sort of interactions. And what I have conveyed to you that how the things go on and how the intensity ratio could be figured it out for a smaller molecule. But if you take the complex larger molecule where manually you cannot fix the intensity ratio, but through simulation you can match it. Okay. But one question came up that day. I cannot remember who asked that question. That normally, while considering the your hyperfine or super hyperfine, we only take into account the constituents having sizable amount of nucleus spin. Okay, and the abundance is sizable. But if the abundance is very little, we normally do not take it into account so seriously, which is difficult, and the interaction would be very feeble in nature. It won't be anyway reasonable to consider. For example, in methyl diadical, one question came up that carbon having 1% C13 carbon always, so that could split the spectrum to a smaller extent. So each line would be further split into two lines. So instead of 4, we may be getting 8 lines. Okay. And then if you go for a splitting pattern, the question was whether should we consider the C13 splitting pattern first or your H3 first. Now C13 splitting pattern cannot be considered over here because of the fact the constituent is only 1%, and even if the interaction is there, that is so feeble, but one can think about it. Okay, so we considered the splitting pattern where your abundancy is quite reasonable, and of course the nucleus spin comes into the picture, the quantum of nucleus spin, that also comes into the picture, and that is why we said all these small lines for the carbon 13. Okay. And then one more issue was highlighted, that electron is residing on a particular atom, and then we are talking about the interaction with the nucleus spin. And that particular atom, if it is nuclear wise active, that interaction obviously is going to happen. There is no second question about that. But the question is, if you have an adjacent atom, that adjacent atom could also participate in the nuclear electronic interactions or not. It depends on mostly the distance. If the distance is too far, naturally that won't come into the picture. Okay, even if the distance is equal, if there are two options are there, then which direction the coupling would be stronger, which is not very easy to make guessing over here. So you need to depend on the simulation over there. For example, in case of ethyl radical I said is a direct couple between the two carbon center. So that would these protons attached to the two carbon, this would anyway come, but the next one would also come, which is being reflected over here. But the complexity arises over here. I already said that thing, that if you look at the number of lines, which suggests 2 into 4, that means 8 lines, right? But one could anticipate also that this proton coupling, but that has not been, observed, and even if it is observed, which hasn't been resolved. So this kind of tricky situation always you will have for a smaller molecule or for a larger molecule also. Similarly, you must have noticed that here the situation is such that not only this nitrogen got involved into the process, but also the protons are involved into the process. We are already discussed. And another issue also we talked about, the resonating configuration, as you see, which makes the things much more complex and all sort of things. So what I'm trying to mean, so these are the kind of issues you need to deal with while while dealing with the EPR spectroscopy for your unknown compounds, and never expect to have the ideal situation. Ideal situation is good for on a piece of paper. Okay, whatever the basic approach is, whatever you have been observing experimentally, try to understand and try to interpret. Okay, now in certain occasions you can interpret in the best possible manner, and certain occasions you are not very happy the way the interpretation comes up, but what to do? Okay, tomorrow someone may come up with a better interpretation, and that's how the science grows. Okay, it's a ladder process. Stepwise, it moves on. Now, and another thing also I said over there, that the resonating configuration, which also allow you to interpret the number of lines, because if you consider these two nitrogens are equivalent, then you will have 5 lines. If it is not so, then you will have 9 lines. Okay, so that means what you have been observing experimentally, then you see how much it is logical in terms of chemistry, that chemically you can generate or develop the logic or not. If you can develop the logic which is accepted, then it's fine. If you cannot develop the logic, then you need to think about a new way to interpret the experimental fact. Experiment is a fact which you cannot alter. You can modify, you can improve by changing the experimental conditions, by changing the instrument sensitivity, and mechanically. But that's a fact at the end of the day. So you have to interpret, and if any limitations based on the instrument or experimental, you have to accept that fact as well. Okay, now this thing we started talking, but we could not explain properly. Now there are a couple of messages over here. It is true that these two nitrogens are equivalent, and then you will be getting naturally 5 lines, and there are 4 equivalent hydrogens, so you will be getting 25 lines. So that is fact. Now here you see that if your molecule is small, and it is true for any understanding of chemistry, the molecule is small, always your understanding would be better. If your molecule is bigger, then your complexity naturally would be proportionately bigger. Okay, so here even we can understand the intensity ratio. For example, you see that these two nitrogen, that means two centers with I equal to 1, N14, I equal to 1, and they are being, they would be giving 5 lines, and the ratio already, our chart, what I have shown, a partial chart, you will be getting the full chart in the literature. Then the ratio is 1, 2, 3, 4, 1, 2, 3, and 2, 1. That depends on how do you distribute the two nucleus spin, up, down, mixed, and all sort of things. Okay, and then this 4 hydrogen, that also we know that how it would be splitted with the I equal to half. We know that 1, 4, 6, 4, 1. That means each line would be splitted into 5. So 5 lines would be splitted into 5 into 5, 25, which is fine, which is matching quite well. Now, if you look at the intensity, there is a beautiful pattern that it grows, and then it starts decreasing. And it is why? because of the fact this is the distribution for the proton, you need to multiply this into this, 2 into this, 3 into this. So you will be reaching maximum 18 here, here 12, here 6, and that is the 18 one. After that again it will be decreased to 12 and then to 6, and that is, I'm talking about the maximum one, and that is why it is happening like this. And that's why EPR looks very symmetric. If ideally it is correct, it looks very symmetric and rather beautiful also. Okay, so this is how one could get some perception how the lines appear and how the intensity distribution takes place. But it is good when easily understandable if your molecule is the smaller one, not the larger one. Now, another example, again, this you will see that both the things are here. I should have shown the color and the black picture together, but anyway, it doesn't matter. You see, experimental and simulated one, it's been plotted for this particular molecule. Now, if you look at, there is a website, it's called the EG Spin, which is available in the public domain. So those who are interested, they can do the simulation by the dotted line is the simulation one. And if you you have to inject the data. If you inject the data appropriately, your simulation would be exceptionally good and almost 1:1 correspondences. If you look at the simulated and experimental one, they are moving exactly parallelly. But if your simulation is not good, that means you cannot manage to do the simulation properly, then it won't match. And if it doesn't match, then after simulation, why you are doing the simulation? You are trying to extract the necessary parameters like G parameters, like A parameters, and so on and so forth. Now, from this spectrum is very difficult. But what you can do, once you have the simulated one, then computer will tell you what is the A parameter, what is the G parameter, what is the splitting parameter, etc., etc. And you have a higher degree of reliability. If they don't synchronize on top of each other, then whatever parameters you will be getting through computational processes, your reliability factor won't be very high. So you need to have 1:1 overlapping. And if you have that kind of spectrum, then you can think about any data you are getting out of your computational process, which is acceptable. People would accept you with a proper reliability factor. Okay. Now, if you take this molecule, it's a very interesting molecule in the sense that you have many options in hand. So you have got a spectrum like around 27, 28 peaks, if I am not wrong. You can count it 1, 2, 3, 4, 5, 6, 7. This way I have counted it. You will get around 27 to 28 peaks. Now, how to interpret this thing? Now, if you consider all the nitrogens are equivalent, then you should expect 9 lines, right? 2 into 4 into 1 plus 1, all N14. Na? So 9 lines. But you are getting 28. So certainly all the nitrogens are not equivalent. Okay. And if you have the crystal structure of this molecule, you could see that nitrogens are not equivalent. Okay. But they would interact with all nitrogen having I equal to 1. They would interact with this unpaired electron. And that would lead to have your super hyperfine splitting and hyperfine splitting both together. Okay, so if you consider this nitrogen, then 3 lines. And this is directly bonded. The second nitrogen would also participate into interactions. Then you will have 3 into 3, 9 lines. But you are getting 27 around lines. That means one more nitrogen is also involved. So this nitrogen must be involved into the process. So 3 into 3 into 3, that means 27 lines you are getting. You are not getting the interactions of this electron with this nitrogen, the fourth nitrogen. Well, how do you interpret it? That is the biggest concern. Looking at this molecule, I don't know how to put it this way. One is ortho, other is meta, other is your para position, other nitrogen. So your experimental result at the X band condition, I have to be very, very clear, at the X band condition, it suggests out of 4 nitrogens, 3 nitrogens are being participating in the MS and MI interaction. Fourth one is not. Now, unfortunately for this molecule, I do not have any data of Q band. Literature, it is not available. Nobody explored that thing so far. Q band and W band spectrum. Now, what will happen in the Q band and W band? Unless we do so, we cannot rule out any remote possibility of the interaction of electron spin with that fourth nitrogen. But as I said, so always once you do the EPR spectrum, EPR experiment like NMR, you have to mention that what machine you have used, so that you have made the things very clear in front of the audience or the readers that this is the condition, this is the results. So if you change the condition, results might vary, and then you have to interpret in a different way. So this is under limited circumstances, this is the best description one could put up, and everybody would accept your argument. Okay, scientific argument I'm talking about. So, but on the other hand, if you move into this molecule, you will see this is the direct, so there is no question of missing. So you will be getting doublet, and then this will be not direct because oxygen has no spin, but one bond gap. So this will be also participating. So you will be getting 2 lines. So total 4 lines will be getting as per the splitting pattern. But this carboxylate, your hydrogen, somehow it is not been participating, as because of the fact one could argue that here it is a direct oxygen bond and that links to your hydrogen, but here distance is longer because it links to carbon, and that carbon is linked to oxygen, and oxygen again linked to hydrogen. So it's a double bond, 2 bond distance is there instead of 1 bond over here. So that's why only this part is interacting, this part, not this part, and you are getting two doublets. Okay, now once you get the 2 doublets, then naturally you will be getting 2 A value. Already I said what is the A value when the lines are getting splitted. Then the difference between the 2 lines, okay, in terms of the magnetic field, that means Gauss, that difference would be considered as your A value. But here though you are getting 4 lines, but essentially you are getting initially 2 lines, and each line is being splitted further into another 2 lines. So that means that one gap is the middle of this one to middle of this one. That means 1.71, MT. Okay, that is one gap, and other A is this one. Okay, that means this coupling is much stronger. This is the 1.71 MT. That is this coupling, this electron and this proton, and this electron and this proton. That coupling is essentially your 0.26 MT. So you have 2 types of coupling parameters, which is called super hyperfine coupling. That is your A factor. Now, if you go into a very simple molecule.
Sir?
Yeah.
Sir, the previous slide.
Yeah.
No, sir, the nitrogen ring. That slide.
Yeah.
Yes, sir, here it also can be happen that we know all that the radical can be resonate. So the R containing 2 nitrogen, they may be similar, and the 2 nitrogen containing the keto group, they may be similar. Then that may be 5 into 5, 25. That also be possible, no, sir?
No, what you say? You repeat it, please. Let me understand.
That the radical resonate.
Yeah.
So that
the problem is these 2 centers are not identical.
No, sir, I don't say that. I say that the nitrogen, if the radical resonate, then the upper 2 nitrogen will be similar.
Okay.
And then there comes the 5 lines, and below the 2 nitrogen, they are also similar if the radical resonate. So
Yeah.
there will be 5 into 5, 25 lines. That also be possible.
Yeah. Well, you are free to think whichever way you like to, but the problem is, if you look at this structure little bit carefully, here, considering this one fragment, which may not be very logical, because electron is essentially localized on this nitrogen center. That is the problem. And if you record the spin density of this molecule, record means calculate, which can be calculated, either Mulliken spin density or Laude spin density. If you calculate, you will see the most of the spin is on this particular nitrogen, because it is essentially, two bonds are there, na? And if you look at here, 1, 2, 3 bonds are there. So even if there is a kind of delocalization, the extent won't be too large. Okay, it will be a very limited extent. And because of the 3 bond nitrogen, this is basically anionic nitrogen. And this, you cannot make it anionic. In order to make the anionic of this nitrogen, either you have to keep this nitrogen carbon bond or this nitrogen bond, then the ring is gone. And this nitrogen carbon bond cleavage is not so easy. Okay. So that shuttling is not possible. From this nitrogen, the methyl group cannot, shuttle from this nitrogen to that nitrogen. Okay. So what one could think about, just that these two nitrogens are different. This is anionic nitrogen. This is neutral nitrogen. All other nitrogens are neutral. So spin density calculation suggests that spin is essentially localized. The partial delocalization at this center or at this center, it is there, but that is not to a large extent. So that is why we need to consider this coupling. This is the orthocoupling, this coupling, metacoupling, which cannot be neglected considering the fact of the experimental results. But the para-coupling, that means 4 distance, 1,4 coupling, which is not being observable, possibly because of the distance. So in EPR, possibly is one of the term one quite often one needs to use it, because you cannot understand what is happening over there. But this is the most logical way to put the argument, not the way you are trying to explain it. I appreciate your thought process, but only problem is this is anionic center, not the other one, the anionic center. Okay.
Sir,
Yeah.
in this only, if we take the Q band, will the CH3 protons also split the signal?
No, that's why I already mentioned that only one data is available in the literature, that is the X band data. So Q band and W band, what will happen, we don't know. Now Q band, most unlikely this proton will come into the picture. I am anticipating that this nitrogen might have been exposed. Okay, because this proton is far away, which won't be taking place. Because as I said, that's another argument. In terms of the previous question, that since it is being localized over here, if it would have been localized over here, then there would have been a possibility in the high frequency part, okay, in the Q band situation. But since it is not that way to move forward, and this CH3, even if you go for Q band, it won't be exposed. Only the likely situation, though it is not known, likely situation is the exposure of this nitrogen in terms of this interaction. Okay.
But CH3 is also like 3 bond only from the N.
No, CH3 you have to understand from this nitrogen center. Is a more of a hypothetical question, because the data is not there, na? So this is my perception that this won't come into the picture. If you go for Q band, this may come into the picture. So unless we do the experiment, we cannot make much of judgment on this molecule. Okay. Now, if you go for this molecule, then I said that there are 2 types of coupling constant you'll be getting. One is the larger one, other is the smaller one. And this is a very simple molecule. And you look at this molecule, it's called the tetrazine. Na? Have you heard the term tetrazine? Is a very interesting molecule from a variety of other consideration. But EPR wise, it looks rather simple to me. The reason is this nitrogen you look at, it is fully delocalized situations with all are equivalent situation. Unlike the previous case, all the 4 nitrogens are not in an equivalent situation. 1 CH, 2 CH3 and all these things are there. But here it is absolutely equivalent in terms of here and in terms of 2,6 substituents also from that point of view. So all 4 are equivalent. So 2 into 4 into 1 plus 1, 9 lines. And we know the distribution pattern. It's just a textbook example. Okay, beautiful textbook example. And the spacings between the 2 lines exactly identical. If you look at a little bit carefully, this is an experiment. This is another experiment which one could consider as a textbook example. Okay, and that means since all the the gaps are identical, that means one gap can represent the whole molecule. So you need not to calculate the A1 to A7 or A8. Only one A if you calculate, then that could represent the A value. And A value tells you, as we have discussed this issue, A represents the extent of interactions of the electron spin with the neighboring nucleus spin. A neighboring could be the part of the same atom carrying the unpaired spin, or the other atom which is linked to the central atom carrying the electron spin. Okay, so this is a very simple, beautiful example. Now, this is one example I would like to tell you. Of course, it requires a lot of other understanding. So, without going all the details, only one message I would like to share with you. It is quite often those who are interacting with the oxygen activation, which is a very important issue in today's context to activate the oxygen, because it is abundant in the nature and it is safe, no environmental problem, etc. etc. Now, oxygen is a triplet molecule. And why triplet? The 2 unpaired electron and the antibonding orbital, like pi-star orbital, and they are not anti-parallel, they are parallel. You can make them anti-parallel, but then you have to apply some energy over there. So energetically uphill process. So the oxygen what we have in the atmosphere, that is triplet, but it can be made singlet under certain circumstances. But the spin wise, okay, if you react the triplet oxygen with one of the NO radicals, this is a radical over here, and then what happens that when they come closer to each other, then they cannot distinguish which one is up and which one is down. Some kind of spin exchange takes place because energetically, which is rather allowed situation. That means the energy which is available in the atmosphere, okay, there's the KT energy what you talk about. That amount of energy is quite good to allow the spin exchange process. And as a result, you will be seeing that 2 down would become 1 up, 1 down. And this will become up to, it doesn't matter for this NO. Initially it was up, now it is down, which could be measured by certain other experiments. But it doesn't matter to this molecule, but it matters a lot to this molecule. Now you are getting triplet to singlet. Okay, and this singlet now could interact to a molecule which is closed cell. Now oxygen normally, not normally, oxygen, since it is triplet, it reacts with a molecule having unpaired spin. It cannot react with a singlet molecule. Singlet means closed cell, where all the electrons are paired up. But if you have a singlet oxygen, okay, singlet oxygen generator is there. Without that, if you can make a singlet oxygen during the course of the reaction through exchange mechanism, then that singlet oxygen can also react with a closed cell molecule. So through EPR one could judge it, because once you move from here to here, you look at the 3 spin situation. So this is triplet, it has its own EPR profile, this is singlet, and at the center point you have a triplet situation. Down, down, up, whether they will couple or not, that's a separate issue. But normal circumstances, you can also think about the triplet situation or your doublet situation. But eventually what you are getting, this is it becomes S equal to 0, and you would be ended up with the doublet situation only. So you are moving from triplet to doublet. So EPR could be followed this sequence of the reactions. Now let us move to the metal complexes. So radical is normally easy to follow, but not necessarily always it is so easy to follow. There are complications, but that complications could be handled if we have the pre-understanding, pre-knowledge, and also if we understand the chemistry of that molecule. Okay, because resonance, when it comes into the picture, our mind needs to function in the direction that what kind of resonating configuration one could conceive as far as that molecule is concerned. So many things you have to consider together, and then you will have a better perceptions or understanding through the EPR or ESR experiments of that radical system. But remember, the radicals what I have talked about so far, which is only doublet situation. That means one unpaired electron is there. Now, there are organic molecules, as I have given you an example in the I think first class. You could think about this molecule. Okay, this is a triplet molecule. Okay, though very unstable, but the EPR could tell you, yes, this is the right situation. One could reach through EPR only. One could tell. No other experiment could help you to understand it, that you are here, because you have two unpaired electron. That means S equal to 1. That is a triplet situation, and its spectral profile would be completely different than any of the items what do have over here, all single electron. But this will be actually resonating form, no unpaired electron. So this form or this form would be completely different with respect to this form. So again, you can have an organic molecule the 3 unpaired electron up instead of down one. Okay, 3 up. Now, if you have a 3 up situation, that will be extraordinarily complex situation. So, well, we should not be afraid of the complex situation. We should only try to understand how to handle the complex situations, right? Okay, but as far as the organic is concerned, which is in general, it is not that difficult, but there are occasions where one needs to also handle the complex situation. For example, I said the triplet situation, which is rather difficult. Now, once you go to the metal system, I'm talking about metal complexes, basic principles are same, because you see that like radical, if you have one unpaired electron, you can think about minus up, plus up, and then that would be splitted based on the hyperfine or super hyperfine. Now you need to always remember the difference between hyperfine and super hyperfine. Don't forget it. Whether you are dealing with the organic molecule or you are dealing with the metal complexes. Okay. So, and then the parameters are more or less same. Your number of lines 2ni plus 1 into 2mi plus 1, so on and so forth. So there won't be much difference. Okay. So principle wise, you need not to be worried. This is how you should continue. Now, let us take few examples. Now, let us begin with the simple example. Now, we have taken one particular metal complex. Of course, metal complex cannot look like this. You have many other ligands over here. Okay, say let us assume it is an octahedrally surrounded compound. That means there are 4 other ligands. Unfortunately, those ligands do not carry any nuclear spin. Hypothetical situation, they do not carry any nuclear spin, and they do not have your unpaired electron only. So our reactive site is only this portion, not that other portion. That's why we have not considered. Now this reactive site, and again hypothetically, that metal contains 1 unpaired electron. So S equal to half, Ms equal to plus minus half, and we have presumed that I of this metal is 0. Okay, so there is no nuclear spin as far as this metal is concerned, and it is connected to the hydride, 2 hydride. And each proton will have I equal to half, and they are equivalent. So as per our convention, so we have to consider 2 into 2 into half plus 1, so total 3 lines, right? And if you look at the splitting pattern is very simple, as we have already talked about, right? So this half, then this will be splitted with the, now here only one thing to remember, these two are equivalent, like your CH3 radical. These two are equivalent, so we need not to consider this plus this. Okay, if you consider this plus this, then that would be different, then it will be 4 lines, right? So you have to consider, like methyl radical, equivalent centers. So 2 into half, that means 1. So total I is equal to number of nuclei, equivalent nuclei, into the nucleus spin. So 2 into that way. So basically you are getting Mi equal to 1. Net Mi I am talking about. So net Mi means 1 means plus minus 1. So in between 0. So it will be splitted like this with the standard protocol. And then you will have the transition based on the fact of delta Mi equal to 0. And you are getting 3 lines. And here you can easily, it's a small molecule, na? You can easily calculate the intensity ratio 1:2:1. Okay. I'm comfortable in dealing with this intensity ratio for small molecules, not for the larger molecules. Okay. Now, if you move from here to a different situation where the same aim without any effective I value, it is connected to the 2 atoms, both are having the same I, but they are different. Right? One is proton you have considered. In other case, you have considered nitrogen 15. This is nitrogen 15. Nitrogen 15 means same I equal to half. I already talked about it earlier. So nitrogen 15 I equal to half. But unlike in the previous situation, you cannot consider equivalent. That means 2 I equal to half. So you have to individually consider it. So that's why individually you are getting 2 lines because of, well, you could see that this is nitrogen 15 initially or hydrogen initially. It's a very debatable situation because it depends on the abundance. It depends on the I size. Now here everything is same. Okay, so only nitrogen, your nitrogen 15 means you have taken the enriched nitrogen 15. Okay, so here your hydrogen is 100%. So naturally it will be first impact over here. It will give you the 2, this thing. Or you can consider otherwise. The nitrogen is a bigger one. Okay, so bigger nitrogen 15, nitrogen size is bigger. So these will first interact because it depends on the electron density with the nucleus spin. If the nucleus size is bigger, so that diffusion would be stronger, and if diffusion stronger means A would be larger. Okay, so that could be the probable situation. So first this will interact, which will give you the 2 lines, and then hydrogen would come into the picture, and this will split these 2 lines, each again 2. Okay, so that means this gap would be your A for nitrogen 15, and this gap would be A for hydrogen. And it is known that the nitrogen hyperfine coupling constant value is more than the proton hyperfine coupling constant. And the splitting pattern, you could remember, you could see that this is 1/2 first, and here you cannot differentiate which one comes first. Okay, so it will be half minus half, and then this will be splitted further. This will be splitted further. So eventual situation is like this, and then it will follow your delta Mi equal to 0, and you will be getting 4 lines. And intensity, if you here also you can calculate the intensity very easily. You will be seeing 1:1:1:1. That means in NMR term, we call it the doublet of doublet. Okay, so this is a situation which quite often we come across, right? Now you see the very standard example that always uh, we we try to do this experiment for our MSc class, first year MSc class, that for ESR respect, this is one of the compounds where you will never miss the ESR. At room temperature, at low temperature, forget about Q band, X band, always you'll be getting beautiful spectrum. That is why it is considered to be one of the standard molecules to show the ESR spectrum to the students. So here you can see the vanadium in the +4 state, okay, and not necessarily it is pentacoordinated. You will have one solvent over here, okay, the coordinating solvent most likely water. Water is there, but that won't contribute towards your EPR profile naturally. But so it's called the vanadil, na? Vanadium oxygen means vanadil. That is the standard inorganic chemistry knowledge. Now, if it is a 4, that means it is scandium, titanium, vanadium, D3S2, total 5 electrons, remove 4, 1 electron, D1, very standard. And then the 1 unpaired electron will be splitted, and then it will be, since it is 7/2, I equal to 7/2, so you can imagine that there will be total 8 lines, single vanadium. So it will be splitted 7/2 to -7/2. This is the splitting pattern. This is a very conventional pattern, opposite to this sign for the lower part, and for the upper part, excited part, the same size, sign wise. And then you see that delta Mi 0, that means 7/2 to, I think there is a mistake over here. This will be 7/2. Please correct it. So it is a wrong way to project it. So that's why it is not 0. I did not notice it earlier, otherwise I would have changed it. But you will be getting this very routine thing. So you will be getting 8 lines. Okay. Now, like the tetragen earlier example from the organic side, what I have given here, it is the inorganic representation of the same thing. There it is a 9 line, so you are getting tetragen case 8A, but here it is 8 lines, so you will be getting 7A, right? The gaps. Now, you see that A1 to A7, and all are essentially identical. If you look at very carefully, though it is not probably the right representation, but they are essentially identical. Okay. If they are not identical, then you cannot consider one to represent the rest. And then you have to, while writing your manuscript, you have to say A1 equal to this, A2 equal to this, A3 equal to this, A4 equal to this, all these things. This is one point to remember. If they are identical, then one could be the representative A for the whole spectrum. If they are not identical for multi-A system, then you have to consider that you have to consider A1 to A7 individually, okay, to represent your spectral profile. But the next question comes, the G value. Now, G value we'll talk later on at length, but what I'm trying to say here, that normally for if they are not identical, then you have to consider each G separately. But let us assume the simplest example, like your previous case of tetragen molecule, that all are same. So one G should represent the whole molecule. Hello. And if you look at this G, we have to consider the G at the center field. Now center field means this is let us assume this is 1000 Gauss, and this is your, let us assume say 3000 Gauss. So what is your difference? 1000 to 3000 means 2000 difference. So you start from here to 1000 here, and then at the center point you consider the point to be calculated for G. So here you will have essentially the H, say let us assume 2050, just hypothetically. The 2000 is the Gauss, is that center point Gauss. Now you have to use one rider. That means one standard. And the standard what you use, I'll talk about it later on. The standard what you will be using, which is having fixed G and fixed H. So then it is very simple. For standard you have fixed G into fixed H. For unknown you have fixed, you got the H from the experiment, and only unknown factor is, let's say, G2. So G2 equal to G1 into H1 by H2, and G1 H1 is the standard value. So if you put little bit of standard within the EPR cavity, what normally people do, this comes along with the instrument. Actually, one doesn't need to be worried, but nowadays it has been modified. So till few years back, people use this kind of situations. I'm telling you that. Oh, this is a long way. You can see the EPR cavity, this golden color. Within this cavity, they put a pinch up. EPR is very sensitive. Pinch up, rider. So when you are scanning, when you are putting your sample tube, and then within this magnetic domain, you have kept little bit of your rider. So the sample spectrum will come the way it has come for vanadium or any other case, and then the rider would also respond. And if the rider responds, say rider, I'm telling you, yeah. Say rider has come over here, somewhere here. You'll see a small peak over here, because rider you have used a very small concentration deliberately, so that the signal won't be very high and it would mask the original signal of your unknown compound. You want to have a very small response, and that would appear over here. So from there also you can back calculate that this is the H for the rider. G already is known. And in this case, you only know the H, not the G, so you can back calculate, and that G could be shown, and the G is coming around very close to the radical value over here. Now, if you take another interesting molecule, this molecule has a lot of things to extend. Say V2O5, vanadium pentoxide. Vanadium pentoxide is not EPR active. Okay, because vanadium is the +5 state, here. So if +5 vanadium, V2 is 10 by 2, 5. Now if it is a 5, that means scandium, titanium, vanadium. So D3S2, so no unpaired electrons, so diameter. Vanadium 5 is a good candidate for vanadium NMR, multinuclear NMR, vanadium, beautiful candidate. But for EPR wise, what happens, if you look at the vanadium structure a little bit carefully, you will be saying there is a defect. And there you have V4 unit is there. But that content is not very large, smaller content. But smaller content is enough. I said, EPR is very, very sensitive. Unlike NMR, very sensitive instrument. So if you have V4, that means again the T1 configuration. But here what happened, there are two vanadiums. If you look at this structure carefully, two vanadium, they are in a very close proximity in the cubic. And then 2 into 2 into 7 by 2, so 15 lines. And you will be getting beautiful 15 lines. Okay, but here the good point is that, which I will talk a little bit later on at length, what you will be getting, 15 lines at the parallel region and 15 lines at the perpendicular region. So what is parallel, what is perpendicular? Essentially the magnetic field what we apply, you have noticed that in EPR that big magnets, big magnetic unit is used. So that means it applies the magnetic field, and that's why the MS or MI gets splitted. Now normally magnetic field what we put up instrumental convention wise, the magnetic field is parallel to the G axis. Okay, now if it is parallel to the G axis, that means X and Y axis is just your perpendicular. Am I right? Now if it is a perpendicular, Now what happened that most of the molecules would try to or would tend to concentrate on the perpendicular direction, not in the direction of the applied magnetic field. So therefore, what will happen that depending on the geometry, particularly that would be reflected very nicely in case of a tetragonally distorted situation, where you have elongated situation or in a compressed situation. And then you will have two sets of lines, one called the parallel lines, other called the perpendicular line. And remember, we'll discuss it later on, that for tetragonally elongated setup, your parallel line, that means that will be at the lower magnetic field and perpendicular line will be the higher magnetic field. But in a compressed situation, the reverse pattern. That means perpendicular line would be at the lower magnetic field and parallel line would be at the higher magnetic field. Okay. And as I said, most of the molecules would be aligned in the direction of the perpendicular, not in the parallel direction, because they would repel each other. So in that consequence, you can easily calculate, and if the situation is like that, well, you could see the tetragonally distorted situation. So you can think about A, B, C or X, Y, Z, and then you can have two sets of unit, one called G parallel and A parallel. That means G parallel means the center point and the distance between the two consecutive lines or successive lines, that is your A parallel. And for the perpendicular side, again, you have to consider the center field magnetic field position to calculate the G value, and correspondingly you would be getting A perpendicular. So what I'm trying to mean, for tetragonally distorted system, you have to always represent your spectral profile in terms of G parallel, G perpendicular, A parallel corresponding to G parallel, and A perpendicular corresponding to. Why I am telling this thing? You see that in science, or in let us assume the science, what you do anywhere in the world, that remains same if the conditions are same, experimental conditions same. It cannot be, the Mumbai result would be different from Delhi result or Calcutta result or US results. Results would be same if the instrument is same and the conditions are same. Okay, so if today you have one standard vanadium 4 divanadium oxo system with a spectral profile of like this, and the G values and A values are such and such. Now tomorrow somebody somewhere in the world, they got one unknown compound and they check the EPR, and they could see, they know that it's a vanadium, and they check that EPR profile is like this and the G values, A values are like this. And then they will go to the database and they will see that similar values are reported for one kind of structures somewhere in the literature. Then they could correlate. They need not to work very hard to figure it out or to show some light about their unknown compound if the data matching is there. So the data is very important. So one should not, your interpretation might be wrong. So there are people in future, they can rectify, they can extend the newer interpretation, nothing wrong. But data has to be very precise. Data cannot be wrong. Okay, so if data is, different data can be obtained for one particular experiment under a different experimental condition, which is fine, but not under the same experimental condition. Data would remain same whatever you are doing across the globe. So one has to be very, very careful. Now this is one unique example, and through this example, now I will talk about that I have been talking last few days, that once we are talking about hyperfine and superfine, super hyperfine coupling in ASR spectroscopy, we talked about the nuclear spin, and we know the nuclear spin depends on quadrupole moment, all sort of things, etc. But fortunately, all the values are available in the literature. You need not to figure it out what is the nuclear spin of copper of this, the 3 by 2, which is known in the literature for all element. All element values are known. People have already done the job for us, so we need not to go. But that's a difficult process to calculate or to figure out the I value. But anyway, now we know for most of the atoms, you have isotopes. Now, these isotopes, normally we do not take into them very seriously. But under certain circumstances, we have no options. We have to take them seriously. And you will see that mass difference is there always in the isotopes. 1 unit, 1 unit. And in the mass spectrometry, once you do it, you will see that it is being very nicely reflected. Okay, that isotopic pattern, etc. But here we are not dealing only the isotopes. We are dealing with the 2-3 factors associated with isotopes. What are those factors? One factor is their natural abundances. Now what happens? You will see 0.01% natural abundance, 0.1% natural abundance, 1% natural abundance, like carbon-13. We don't take that very seriously, and mostly they are not very stable situation. Okay, but if it happens that sizable amount of natural abundances of many isotopes for a particular atom there, then we have to be very careful. Now, depending on what spectroscopic technique you are choosing, their requirements are different. For ESR wise, the two requirements are there. For mass wise, only the natural abundance quantum is important. For ESR wise, the natural abundance quantum is important. On top of that, your nuclear spin is also important, which is not because is a nuclear interaction is there with the electronic interaction, which is not necessary for mass spectrometry, right? So one such example, if you look at the simple copper tetracoordinated copper square planar compound, copper 2 of course, because acetyl acetonate 1 minus, and this is a resonating form 1 minus, so copper 2 neutral compound D9, 1 unpaired electron naturally. And that gives you one line spectrum, which is not equal to the radical spectrum. Now, let me tell you this. I think I should have told you this thing earlier. Now, in a metal complex, radical you get one line. Normally, if there is no hyperfine or super hyperfine interaction, you will be getting one line EPS spectrum. In a metal complex, if it's a perfectly symmetrical system, there is no distortion along the XYZ axis, then you will be also getting isotropic signal, one line spectrum. Now, looking at one line spectrum from your compound, one could be, misinterpreted or could be confused whether it's a metal based or ligand. If you know your molecule, sometimes what happens, the segregation between metal and ligand takes place, the bond rupturing takes place. Then the EPR response, what we would be getting could be, who knows, could be one radical response. Now, then if you get a one-line spectrum, then particularly in the solid state, always in a metal complex, you'll be getting one-line spectrum. You won't get any splitting due to the molecular distortion. Then is it appearing due to metal or due to ligand or radical? How do you differentiate it? Yes, remember, the ESR line width is very important to distinguish between metal and ligand. For example, line width means that difference in magnetic field between the two peaks. Okay, so you can extend one line along this, maximum, and another line along this maximum, and then the difference between the two maxima, that is your line width. Now, if it is a free radical, you will be getting always very sharp, 2 to 10 Gauss, roughly, the line, maximum 2 to 10 Gauss. But for a metal complex, even if you get one line, due to the lack of any anisotropy, but the gap would be 40 to 100 to 100. So that but again, one could argue, visually you cannot differentiate, because if you squeeze the scale along the x-axis, then one broad spectrum would be looking sharper. Or one sharp spectrum, if you expand the x-axis, that would be looking broader. Okay. So by looking wise, you cannot differentiate. You have to calculate the peak-to-peak separation up and down. Then it doesn't matter whether you are plotting in a squeeze fashion or in an expansion fashion, expanded fashion, right? So if you have that peak-to-peak separation, and that would tell you that whether it is a ligand-based or metal-based or not. Remember that point. So that you cannot be confused ever in life. Now, if you have a molecule of this, and if you look at the copper, so one line would be splitted by I equal to 3 by 2, right? Okay, so all of you know that copper having I equal to 3 by 2, and which is a large percentage. Yeah? Large percentage means if we combine these two isotopes, is almost 100%, right? So there is no question of missing copper hyperfine coupling. We are not considering any super hyperfine because here oxygen, carbon, they cannot take part, hydrogen is far away, etc. But again, if we record the spectrum of this compound, where there is no tetragonal distortion, you will be getting 4 lines, right? Now, if you carefully look at these 4 lines, then the 2 extreme lines, you will be getting a kind of folded line. That means there are 2 lines which are coupled together. Here it is rather clearer, right? So that means it gives you, normally we don't care, it doesn't matter. I got 4 lines, so it is coupled to, matter is over. But it's not over. You have to understand that why you are getting folding over here. Here the line is little bit broader than what one could anticipate otherwise. Okay, and here you are getting clear-cut 2 peaks. So from what is the origin of this peak? That is the understanding we have. Then you have to go back into the isotope, as I mentioned you just now, the ratio of abundances of the isotopes. Now there are 2 isotopes. Here the good point is both having the same I value. So normally you don't distinguish, but if necessary, if you have a situation like this, then one is 70%, other is a 30%, almost, or say 1:2 ratio. They are there. So ideally, I told you that ideal situation is fine for the piece of a paper, but not for the real situation. Ideally, one should expect spectrum like this, the 4 lines for 63, and these smaller 4 lines for 65. Okay, they should come very close to each other naturally. And if you look at the intensity ratio, more or less half. And here it should be half, as because both having the same number of peaks, 4. Okay, 4 only, their ratio is close to 1.2, slightly here and there, and that's why this ratio would be 1.2. And actually what you have been noticing, we're not getting the exact thing what one could think in terms of reality, but you are getting overlapping peaks over here. Okay, it's not well resolved thing. But if you change the solvent, if you change the glassy conditions, if you change the instruments, and then something better, closer to the ideal situation may appear, I don't know. But this is how one has to be very clear. And if it is so, then A corresponding to 65 copper. And the G value you cannot differentiate much, even if it will be in the second digit or third digit, which is of no meaning. But for the academic sense, I don't know, unless you resolve these 2 separately, you cannot differentiate it. So one has to be very, very careful for the isotope pattern wise. Now you consider another 2 examples. Here these examples are different. Different in the sense that here you are considering more I think 94 or 96, the major isotope constituents total is around 70%. Okay, and that I equal to 0. Now, if I equal to 0, and if you take platinum 3 compounds, a D7 compound, okay, or if you consider platinum 5, okay, so then you will have one unpaired electron, and that unpaired electron would give you one isotropic signal. I told you previously that if you do not have molecular distortion, then your metal-based unpaired electron, one electron, would give you radical type of spectrum. Only difference would be the line width difference from here to here, okay, between the two maxima in terms of Gauss, that would be broader compared to the radical. So essentially you are getting one line, okay, but if you look at the actual spectrum, you have one central line, and on both the sides you have two spikes. It's not exactly spike, but the two spikes type of lines. So from here it is originating. Then if you go back to the isotope pattern, then there is one stable isotope, 195, and that around 34%. So you cannot ignore it. And I equal to half. I equal to half means, that means you will have two lines, two extra lines. So these two lines, what you are getting, essentially they are originating out of this platinum 195, I equal to half, 34%. Now, ideally, if you consider this is one line and then there are two more lines, and the ratio would be, this is 1 and ratio would be 0.3, that means 34% by 2 in comparison to this one, relative to the I equal to 0. I equal to 0, 66, that is 100%. Nah? And here, because one line you are getting. And here you are getting that natural abundance is 34%, and your compared to total 34%, and instead of one line you are getting two lines, so you would divide it by 2, then 17 times smaller compared to your the central I equal to 0 containing line. Similarly, if you go for molybdenum, you will be seeing that molybdenum 5 compound, that is molybdenum is scandium, titanium, chromium. Okay, so no, vanadium, chromium. Chromium, below chromium is molybdenum, that means D4S2. D4S2 if you take, and then molybdenum 5 if you take, that means you are getting essentially D1 setup. And if your molybdenum isotope distribution 95, 97, you see I equal to 5 by 2, total 26%, this two. And you have 94 and 96, they are around your 75% or 74%, there is no I value. And if you take one molecule where there is no distortion, deliberately have to take to understand this picture. If you take molecular distortion, you cannot get the right feelings how the isotopic abundance and their I values would impact on the EPR profile. You will not understand. So to understand one particular is 26%, Moly 95 and 97. But the rest of the Moly 94 and 96, that means 74%, one line. So you have one sharp line, and on both the sides you have the total 6 lines. If you can see 1, 2, 3, 4, 5, 6 lines. That 6 lines is coming out of this 5 by 2 I. Okay. And if you look at the ratio, then ratio would be, so this is 1 versus 6, right? And that means 26%. So 26 by 6, that means 4% of the original line. Original line where it is 74. In the previous case, copper case, we have only divided this by this, right? So that was 70%, this was 30% or 65%, so almost 2 ratio. But here, because they are both the cases I equal to 3 by 2, 4 lines plus 4 lines. But here 1 versus 6, 1 versus 2. So the ratio not only would be this one, but also the number of lines with respect to the parent line, that is one line. So this is, in this case, it is 34 by 2, so 17 times smaller. And here it will be that 4% of the original line. So very small actually. Okay. So actual spectrum, if you look at it, is rather very small. But you won't miss it. That is the important thing. You won't miss it. Now another beautiful example. I like this example because if you see, there are many issues are involved. EPR is rather complex in understanding compared to NMR. NMR is beautiful for molecular structural design. Electronic structural aspects are always difficult to follow, but one could understand to a large extent, that I would say. Now, if you look at this molecule, it is, you could guess what this molecule means. Chromium triple bond nitrogen. Any of you could answer it? What it's called? Do you know that that metal triple bond nitrogen? What it? How it is being defined? Any of you could help me?
Carbine.
Carbine.
Metal either cyanide or nitrile or something.
Cyanide. Cyanide to this
No,
one.
not cyanide. Metal nitrile or something. I kind of forgot the name.
Nitrile. Nitrile to three double bond N. And who said carbide or carbine something? Someone said na. So any of you can suggest something? C triple bond N.
Nitrido, sir. Nitrido.
It's called nitrene. 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 So it's 3 minus actually. Yeah. It's a potent pi donor site. So it always stabilizes metal in the very high oxidation. If you want to stabilize metal in a unusually high oxidation state, you have to use one potent pi donor site. Either metal oxo you have to use. You have noticed the vanadil. Or any high oxidation state metal complexes are oxides normally. Or you can use nitrene, or you can use imido. Imido, of course, 2 minus, and nitrene is 3 minus. So if it is 3 minus, that means you will have 8, total 8 minus, and chromium 5, so overall 3 minus, right? And chromium 5 means D1 system. Now, the thing is, it is very interesting spectrum. Let us first consider the normal way that this chromium is attached to the carbon center. So carbon does not have any nuclear spin, but see, then cyanide means triple bond N is far away. So that impact won't be reaching over here. What impact would be there? The directly bonded nitrogen over here. The nitrene is directly bonded over here, and nitrogen is a N14. So your 1 and 1 I equal to 1, and I equal to 1 means 100% its abundance. So you will never miss it. That means one line, and if you look at this molecule, it is more or less symmetric molecule except this side. So you will be getting basically one line spectrum would be split into 3 lines, and that is indeed happening over here. 3 lines, 1:1:1 intensity ratio. Okay, don't concentrate on this part first. First, let us concentrate on this section. So if you look at this section, that means one line is being split into 3 lines. And unlike all other previous examples, what we have talked about, this is a unique example. Unique example in the sense the ligand is active ligand, which is directly linked to the metal centers. So if it has been directly linked to the metal center and that has been depicted, so it actually proves why the consideration of crystal field was wrong. You go back to the coordination chemistry early stage that it says the crystal field theory, na? And then the ligand field theory came into the picture, or molecular orbital theory. Now, if you look at crystal field theory, what was the need to the ligand field theory to appear? It appeared as because of the fact the crystal field could not explain the color. Okay, crystal field could not explain the spectral feature. Okay, and magnetism also in some extent. So that's why they felt the crystal field was very good when nothing was there. People used to depend on the valence bond theory, but valence bond theory could not explain between the weak field, strong field, all sort of things. But then crystal field theory came, and crystal field theory was very popular for 100 years. And then slowly people realized that it is not complete. And that's why the modern concept of molecular orbital theory came into the picture. And one of the drawbacks of crystal field theory was its initial assumption. It considered no metal ligand interaction, bonding. It only considers some kind of electrostatic interaction. Ligand comes from the infinite distance and it comes to the metal field, and then some electrostatic interaction between cationic and anionic things takes place, but no orbital overlap. Orbital concept was not there actually that time. So orbital overlapping was not there. So this is one of the examples. I'm talking about one of the pioneering example. Via EPR, one could establish the ligand field theory is the validity of the ligand field theory, where it considered the overlapping, the frontier orbital overlapping of metal and ligand, right? And if it was not there, then this line would not have been splitted into 3 lines, right? So this line is being splitted into 3 lines because of this interaction. Now, how did that hyperfine interaction, which is very easy to understand because it is considering the same atom, right? But super hyperfine, it is considering the 2 different atoms, and how these 2 different atoms would interact. They cannot interact through space, right? They only interact through bond. Now, through bond interaction means that there is some kind of covalency. That is the sharing of the 2 orbitals, and that's why you get single bond, double bond, triple bond, and all these things. And electrostatic interaction means they don't come very close to each other, but they do come up to a distance through which they can see their face. Okay, so they can interact. That's a electrostatic interaction. It's called cation and anion. But the covalency says no, it is not so. It is actually the overlapping of orbitals. And that's why we call they are within the bonding distance. And bonding distance, depending on metal ligand bonding, if it is a single bond, if it is a double bond, if it is triple bond, accordingly the bond distance starts shrinking, right? Okay, triple bond is much shorter than the single bond. So this is one of the examples which proves the validity of the ligand field theory, fact that the crystal field theory was not correct. Anyway, now what happens? So these 3 lines you are getting because of these interactions, but it shows another 4 lines and smaller 4 lines, and each of the 4 lines, you see, it gets splitted into 3 lines. What is happening over here? That there is one isotope of chromium, that original isotope, I think chromium 54 or 55, I forgotten. So that does not have any I value. So this splitting is only due to the super hyperfine disk coupling. And then what happened? The 10% chromium 53, that is also stable isotope, which is having I equal to 3/2. So I equal to 3/2, only 10%. That means the one line is being splitted into 4 lines, right? And these 4 lines, what is happening over here, their then distribution would be actually your 10 by 3 by 3 lines, each 3 lines, so 10 by 3, very small lines, and then each of the lines naturally would be interacting with this. Okay, no, 4 by 4 it will be, yeah. So each of the lines would be again interacting with this nitrogen center, and then you are getting 3 lines. So this strong line corresponds to I equal to 0, the splitting due to the metal nitrogen interactions, and these 4 lines appearing because of the 10% chromium 53 I equal to 3 by 2, and that ratio would be very small, and which is in fact so. And then each of these lines would be there, the part of the chromium, and there this chromium triple bond nitrogen is there, and that would interact with each other, and that would give you the 3 lines, small super hyperfine interactions for the other isotopes. Okay, now do you have time, or I should stop here?
Sir, our another class is already started.
Hey,
So
it didn't already start, because now it is only 29:30. Okay, okay. See you tomorrow. Next day. Bye.
okay, thank you, sir.
Thank you.